In the previous video, we learned that there's three basic types of bonding. And from here forward for the remainder of the unit, we're really going to focus on ionic bonding. And when we're going to focus on ionic bonding, we need to learn about something called an ion. Now on the screen right now, you're seeing all of the different subtopics that we'll learn about in this series of videos. But for the purpose of this video, I really just want to focus in on one of these topics, and that would be ions, what they are, and why they form. So let's review a couple things before we get started. Now, way back in the beginning of our unit here, we learned that there were three subatomic particles: protons, neutrons, electrons. We know where they live, we know what kind of charges they have, and what masses they have. But what we might not be thinking of is what they control about the functions, about the personality of these atoms. Now, protons are the most important particle. If you change the number of protons on the inside of an atom, you're going to get a completely new element. This is why the periodic table of the elements even exists. They are in order of the number of protons that are inside of the nucleus. We also learned about neutrons. When you change the number of neutrons on the inside of an element, you don't change what that element is, but you do get something called an isotope. You can almost think about these like atoms being a little bit chubbier or a little bit skinnier than their normal selves. And that's okay. We'll learn a little bit more about isotopes later on in this year. Electrons. This is new. If you change the number of electrons on the inside of an atom, it's still going to be the same element, but now it's something called an ion. Now, an ion is an atom that has the same number of protons. It can't even have the same number of neutrons, but the one particle that will be different is the number of electrons. And there's a very specific reason as to why atoms form ions. What I'd like you to think of an ion is right now is simply an atom that has a charge. You have an imbalance between the number of positive protons and the number of negative electrons. Before we go on, I think it's also really important for you to understand that ions are not ever formed by changing the number of protons. If you change the number of protons, you change what element that you're dealing with. That completely changes the atom. If you change the number of electrons, you still have the same atom, but now it's going to have a charge. So we only ever create charge imbalance by changing the number of electrons. So how and why do atoms actually become ions? Well, there was a lot of research very early on in atomic theory done about why and how all of the different electrons behave the way that they do. And while that research was happening, a very important law was actually formulated. We call it the octet rule. You may have learned this as 8 is great, but 2 will do. That's a pretty important phrase to have in the back of your mind. The octet rule simply states this: an atom tends to be very stable when its valence shell of electrons is completely full. Now don't forget, valence means outer shell. So when its outer shell of electrons is completely full. Now, what about the 2 will do? Some atoms are so tiny that they actually can't fit 8 electrons in their valence shell. And I'm thinking specifically of hydrogen and helium. They're considered to be completely full of electrons when they have 2 electrons in their valence shell. So 8 is great, but 2 will do, but only for hydrogen and helium. Now, this slide's going to look a little bit scary, but hang with me. We're going to make it through here. I want to take a look at the electron configurations of a group of elements. That would be lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. And before you start thinking that I picked them randomly, I did not. Take a look at where they're located on the periodic table. They all come from the second row, straight across on the periodic table. That means that their valence shells are all going to be the second shell of electrons, but they will have a different number of electrons. I want to see what the trend is as we move from left to right across the periodic table. Now thinking about this stability thing, thinking about 8 is great, but 2 will do. So let's get these electron configurations jotted down on our lovely little chart here. I would suggest practicing writing out your own electron configurations, hitting pause here for just a moment, and then push play and we'll resume and I'll show you what these electron configurations are. So welcome back, and let's take a look at these lovely electron configurations. Hopefully they match up with what you've written out. So let's start taking a look at lithium. Lithium's electron configuration is 1s2, 2s1. Our first job is to identify the valence shell. Now that's going to be the shell with the highest number, the big coefficient, out in front of the letters. And for this case, it looks like it's going to be the second shell. So there's my valence shell. In this case, I only have a 2s1 electron. That means it only has one valence electron. Now, lithium has some choices. It can get to a full valence shell by doing one of two things. It can either choose to lose that one electron, exposing a full shell underneath it, or it can fill up the shell that it has. But in this case, it will need to gain 7 electrons to fill up that outer shell, to fill up that outer 2 shell. Now, atoms are just like we are. They don't like to do more work than what's necessary. So they're going to take the path of least resistance here. And in this case, that means that it's going to choose to lose 1 electron. So as lithium becomes an ion, the easiest thing for it to do is to lose its 1 valence electron, exposing a full shell of electrons underneath. Now let's fix that electron configuration for when lithium is an ion. It would look like this, simply 1s2. And it would have a charge now. Now lithium just lost 1 electron. Electrons have negative charges. So if a negative charge leaves, what's left behind? A positive charge. So lithium's official charge now as an ion is +1 because it lost 1 electron, and my electrons and my protons are now out of balance. I have 1 more proton than I have electrons, +1. All right, let's do the same thing with beryllium. Let's first identify that valence shell. Looks like the biggest shell number is 2, so there's my valence electrons. I have 2 s electrons in the second valence shell, the outermost shell. That means I'm either going to have to lose 2 or gain 6 to fill up that shell. I can either lose the shell completely and deal with a full shell underneath it, or gain 6 to fill up the shell. Easiest is to lose those 2. Now let's fix that electron configuration, and you'll notice that it should be pretty similar. 1s2. Now, because I've lost 2 negative charges, I need to figure out what the overall charge of my ion is going to be. If I lose 2 negatives, 2 positive charges are left in its place. So I should have a +2 charge overall. Now the remainder here should get just a tiny little bit easier. I'm hoping you're starting to see the pattern. For boron, let's identify the valence shell. That's anything in the second shell. So my valence shell consists of 2s2, 2p1, 2 subshells, but they still make up the valence shell. That means that boron has a total of 3 valence electrons. So you can either lose 3 or gain 5 to get up to that octet. Again, the easiest option here is just to lose those 3. And let's fix that electron configuration. Again, it turns into 1s2. If you lose 3 negative charges, you're left with a +3 charge. So boron, if it chooses to become an ion, becomes a +3 charged ion. Carbon's going to be a little bit interesting. Again, we're going to identify that valence shell as anything in the second shell. That means it has 2 choices, gain 4 or lose 4. Well, if you're having trouble deciding, so am I, because this is an even split. So it chooses kind of to do neither. We'll actually see carbon more involved in covalent bonding rather than ionic bonding. It doesn't typically like to form an ion. So we're going to skip this and skip the identification of its charge. Let's keep moving. Nitrogen. Nitrogen, here's its valence shell. You can see it has 5 valence electrons. So it can either choose to lose 5 or gain 3. In this case, it's actually going to be easier for nitrogen to gain 3 electrons. Let's fix that electron configuration, adding 3 electrons into it. It's now going to become 1s2, 2s2, 2p6. Now nitrogen just gained 3 negative charges with no protons to balance it out. So nitrogen's charge, when it becomes an ion, is actually a -3. Same process with a little more speed now. Oxygen, here's its valence shell. You can see it has 6 valence electrons. So oxygen can either lose 6 or gain 2. It's going to choose to gain 2 because it's the easier, simpler path. We fix the valence electron configuration here. Eerily, it also looks like 1s2, 2s2, 2p6. It's just gained 2 electrons with no protons to balance it out. Its charge, -2. Same thing with fluorine, has 7 valence electrons, so it can either lose 7 or gain 1. Easiest solution is to gain that 1, so we'll fix that electron configuration and now assign its charge. It just gained 1 electron without a proton to balance it out. Overall charge is -1. Take a look at that beautiful pattern that's emerging. And then finally, neon has 8 valence electrons, so it can either choose to lose 8 or gain nothing. I think we all know what it's going to do. Gain nothing, because it's already perfect. So its electron configuration does not change, and we would actually assign it its normal neutral charge, a charge of 0. Pretty interesting stuff. Now, before we leave this chart, there's something I do want to point out to you. Did you notice that all of these electron configurations are the same, even though they're not the same atom or ion? And what about these? Did you notice that they're all the same as well? Well, they're the same because they're stable. They're completely full. And although they're not the same atom, we would call these things that have the same electron configuration isoelectric. Isoelectric means that they can be different atoms, but they do have the same electron configuration. So when these items are ions, they do gain the same electron configuration. They are isoelectric. One more thing. Let's unpack all this information and plot this on a periodic table, because remember, this is a trend. So here is my handy dandy periodic table. And the first thing I want to track are the valence electrons. Maybe you remember how many valence electrons everything had as we moved across the periodic table. Here they are. Going straight across, it's just 1, 2, 3, 4, 5, 6, 7, 8. And notice that I skipped the transition metals. Well, that's for a good reason. They actually have a variable number of valence electrons, and that depends on a number of different factors. We'll learn about that a little bit later. Now, let's go back over those ion charges. Going straight across the periodic table, I have a little silly phrase that I like to use as I go through to help me remember. +1, +2, +3, skip. -3, -2, -1, zip. The noble gases will always have a neutral charge because they are completely filled up and stable. Those transition metals, again, they're going to have variable charges because their electron configurations are also a little variable. More on that later. This is really important to get down in your notes, so if you might want to pause this screen right now and make sure that you have this jotted down somewhere. A little bit more. We have 2 terms here that you desperately need to know. Cation and anion. That's not cation and anion, which is commonly mispronounced by most students. A cation is what we call any positive ion, and an anion is what we typically call any negative ion. Cations tend to be metals, and they always have a positive charge, and anions tend to be nonmetals, and they typically have a negative charge. One more thing to kind of point out before we completely leave this section. There are 2 different types of ions, and right now you've only seen one, monatomic ions. Those are ions that only are made up of 1 atom at a time. But we will learn about a group of ions that are made of more than 1 atom at a time. They are called the polyatomic ions. But we'll talk about that in a subsequent unit. For right now, it's really important that you understand why atoms become ions, so that they have that octet in their valence shell, and what their common charges are. Make sure you have diligent notes, and I'll see you in practice.